Now that we have our V naught, we can use conservation of energy between our initial position and our final position on the loop. So we know that initially there is some kinetic energy and some gravitational potential energy. And at the final position, we will also have some kinetic energy, and we'll also have some gravitational potential energies. We'll have to assume for this problem that the ball is not rotating, otherwise we would have to count for rotational energy. We also have to assume that there's no friction if the ball is sliding, because if there was friction, then we would have a non-conservative force, which would decrease our total energy. So with these assumptions, we can go ahead and break out what these variables equal, which is 1/2 mv naught squared plus mass times gravity times height equals the 1/2 mv final squared plus mgh final. Now we can go ahead and cancel out our masses and divide or multiply everything by 2, and we get that the v naught squared equals, or v naught squared plus 2gh equals v final squared plus 2gh final. Now we want to solve for this v final so that we can use it to get in our force balance to find the normal force. So to do that, we'll have to rearrange for v final. Now we can go ahead and plug in our value we calculated for v naught. Now our h initial is the full height of the cliff, and our h final will be where the ball is at final, which is at the top of the loop, which will be 2 times the radius. Since the radius is 2.5, it'll be up 5 meters from the reference point, which will have the reference be this surface. And that gives us a velocity final of 34.31.